Hi, this is Jeff Coronado from JCSE, and this is a session in Bridging the Gap. Okay, let's see here. Okay, so in particular here, we're going to focus on WTRUSS1. So the session title is WTRUSS1-1. We're going to attempt to answer a couple questions here. What is a beam? What is a truss, and what's the difference? Which, by the way, I think all of those are kind of fairly valid questions, right? And we'll get to that in a second. But for those of you that are in-house, you can follow along with in WTRUSS1. So getting started here, a truss is a beam. Okay, well, truss is a beam. So what exactly is a beam? And there was a Supreme Court justice of the United States that once said, I don't know how to define it. I don't know how to define it, but I know it when I see it. And I think that kind of fits the category, or beams kind of fit into that category, right? I think a lot of us kind of intuitively know what a beam is, but don't quite know how to actually describe it. Okay, so let's focus on trying to define a beam for our purposes. So a beam has two characteristics. Okay, fair enough. All right, the first thing is that a beam is a horizontal member, right? So these are like schematic representations. If we use these as schematic representations, um, would we agree that that's a beam? It's a horizontal member. So sure, right? That one is a beam. If we were to say here, if we were to look at this one and say, is that a beam? Pretty clearly that one's vertical, right? I think most of us would intuitively say that's a column. If we look at this one, would we say that's a beam? Yeah, it's essentially horizontal, right? It's essentially horizontal. So it is essentially a beam. All right. So a beam is an element that is oriented horizontally. Clear here. Scroll down. Okay. Second aspect of a beam. A beam resists some of the weight. Change this. So a beam resists some of the weight of a floor or a roof, depending on where the beam is placed. Okay, so if the beam is placed on a floor, if it's part of the floor framing, it resists some of the floor weight, then that constitutes a beam. It's resisting weight. Um, and likewise for a roof. And that's kind of depicted here with these gold arrows, right? See those gold arrows? Those are forces. Those represent forces acting downward, as in the way the force due to weight acts. It's a downward force. So beams have that other kind of characteristic, if you will, in that a beam is a member that is oriented uh, horizontally. So that represents, so this horizontal double-sided arrow is kind of the long axis of the member, what we would call the longitudinal axis. It's the long axis of the member, but the loading, again, the loading on it is perpendicular to the long axis of the member. Along the length of the member. And that's the other kind of characteristic of a beam. Okay, so what do we have for a beam? So we've got horizontal member, and it resists weight acting perpendicular to its long axis. That's a simple way to think of a beam. Um, is that completely accurate? So let me do this. All right, so is that completely accurate? some of you might be kind of spinning your wheels. I can see you kind of spinning your wheels in your head and going, well, what about beams that resist axial loading? What about beam columns? Yeah, there can be other aspects to a beam, but I think that's a fight for another day. Okay, for right now, for our purposes, for the purposes of WTRUSS1, I think we can think of a beam in this fashion. Okay, with those two characteristics. So with that said, now let's go back and take a look at a truss. So we're saying that a truss is a beam. So much of our understanding of beams also applies to trusses, all right? In that they are essentially horizontally oriented. If you look at the totality of the assembly of a truss, it's oriented horizontally. And it is supporting, like just like a beam, it supports loading along its long longitudinal direction. It supports loading perpendicular to that longitudinal direction, meaning it supports weight, whether it's the weight of floor, weight of roof, wherever it is that the truss is located. All right, so with that said, how's a truss different than a beam? Right, well, let's bite, right? Let's take a look at that. How's a truss different than a beam? Okay, let's first back up and focus again on a beam. Let's think of a beam, um, and intuitively, we know that as a beam gets longer and as beams support more weight, they need to get bigger. Okay. I think we can intuitively accept that. If we have a beam that's a certain length, we're going to need that beam to be, and this is like if we were looking at the beam from the side, right? This is the length of the beam. So if we look at this as the length of the beam, here's our beam representation. If we have a certain length beam, it has to be a certain width, it has to be a certain depth, right? It has to be a certain size. Now, if we double the span of that beam, right? So if we double the span of that beam, or if we increase significantly the weight on that beam, well, we know the beam has to get larger, right? Intuitively, I think we can accept that. The beam has to get larger, and so forth, right? The longer that beam gets, the more weight that it's supporting, the bigger the beam has to get. Um, there comes a point, where spans are so long and maybe the loading on the beam gets to be so large that a conventional beam is no longer the more cost-effective way to go, right? If you start getting, imagine a beam that's going to be spanning 40, 50, 60 feet, right? At some point, the distance gets so crazy long that a beam would just have to be so humongous that it's just not practical, not realistic. So now let's look a little bit at the behavior of a beam. Okay. Let's look, let's look at the behavior of a beam here. So let me see. Yeah, this is good. So the most heavily stressed, if we think of a beam as just composed of a lot of fibers, just so that we can use that terminology, if we can think of the beam being made up of a lot of fibers, it is the fibers along the top of the beam, along the bottom of the beam, and along the edges that are the most highly stressed. Okay? Those are the fibers that are most highly stressed. What a truss does is that it takes advantage of those principles that I just mentioned and places material in the zones that have the highest internal stresses while conserving materials in the rest of the regions. So what we do is the truss takes advantage of those principles, um, And let me use here maybe orange. And since remember where I squiggled in red is the highest stressed regions. So we're going to put a solid element across there. I'm going to put a solid element across here. Maybe one here, maybe here also. And then we're going to place some other members that are strategically placed. If we start doing something like that, what do we get? We get a truss, right? That's kind of what we're showing down here. This truss in blue, the elements that are drawn in blue represent a truss, make up a truss. It replaces what would have been a humongous beam, but with the savings, with a significant amount of material savings, because we don't have material in here. We don't have material in here or here, right? What we have is simply material across the top, across the bottom, and at strategically located locations internally to that. Okay, so there is our truss. So we can think of a truss, back to red here, if I can. Okay, so what we have is that a truss is a perforated beam, right? I know that there's some simplifications we're making in this, but essentially that's how we can think of it. It's a perforated beam. It is a beam, has a character, it serves the same purpose as a beam, but with a lot of savings in materials, right? So a truss is a perforated beam. A lot of the rules that apply to beams, such as live loads, live loading, tributary areas, live load reductions, also apply to trusses. Okay. And I think with that, we're done. We've now covered WTRUSS1. All right. Thank you, guys.